It is my pleasure to introduce our keynote speaker, Dr. Reinaldo Valenzuela, Director of Wireless Communications Research at Bell Lab and a distinguished member of technical staff. Reinaldo has been at the forefront of many recent advances in wireless in areas such as propagation measurements in channel models, MIMO, space-time systems, transmit and receive arrays, and next-generation air interface techniques and architectures. He's the author of more than 185 papers. He has 44 patents and more than 20,000 citations on Google Scholar. And among many other honors and awards, Reinaldo is an IEEE Fellow and a Bell Labs Fellow. For his pioneering contributions to MIMO technology, Reinaldo has been awarded the 2010 IEEE Eric Sumner Award. Please welcome Dr. Reinaldo Valenzuela.
Alex, thank you very much, and thank you all for having me here. It's a pleasure to be in the neighborhood. I always think of taking advantage and visiting more often, given the proximity. Let's make a mutual promise to do so. Please, let's try to make this more participation-oriented. Feel free to interrupt and make questions. You don't have to write them down, and by the end of the talk, perhaps the question is forgotten. So the talk is about 5G, but please take it as my personal views. I'm not a spokesperson for Bell Labs, let alone the corporation. And in the theme or in the style of scholarly pursuit, let's just have a fun, intellectually motivating conversation about what 5G may be all about. Oh, okay, that would work. So I am not going to bore you with the same old platitudes about 5G, because really what's been happening is that nobody has a clue, and I don't have any clue either. And so everybody's throwing every single wish list to the blackboard and calling it 5G. Well, in terms of maximum entropy, there is no information there. So my bet is 4G is got plenty of shelf life. We haven't even started to stress it with the new applications that the digital life, whether professional, personal, social, will generate. And when those pressures start to really provide a view into revenue streams as well as performance metrics that are relevant, then we'll know out of this, you've seen this circle that has all of these spokes. One is 10 gigabits per second, 1 millisecond latency, 20 years battery life, 30 dB more link budget, et cetera, et cetera. Well, they are correct in the sense that at least one of those spokes is going to actually be a requirement that is really needed and supported by a realistic business case. But we're not there yet. So having all spokes tells me we really don't know which way it's going. So with that, what do we do as researchers? Well, let's step back and let's have a conversation about technologies, some you heard this morning, that may give us advantage on which we can build something interesting. So while we wait for the exciting new applications and the digital life, as I call it, to show the path through the customer pool, let's do a little bit of a technology pool. And so I'm going to jump right ahead onto a topic that is discussed very much in 5G discussions. So the last two slides you saw are the ones that you've seen over and over again about what 5G really could mean. And again, I'm not going to spend a lot of time on that. I really want to spend more time on millimeter wave. Okay, here is something technology-based that us engineers may want to spend some time on. initially, I confess, I started extremely skeptic, coming from a 20+ year background on 2 gigahertz, 900 megahertz, antennas that are close to 2 meter high, 50 centimeter wide, weight 80 pounds, and knowing that increasing frequency will introduce free space loss proportional to the frequency ratio squared, and so you're going to need tremendous amount of antenna gain. How are we going to do this? Does it even begin to make sense? Well, while we wait again for real new exciting revenue generating lifestyles, professional and otherwise, why don't we give it a serious look? And to be honest with you, there are a number of entities, including across the water over there, where a lot of action. And so is this action justified, or is purely an academic pursuit? So clearly the reasons are there is tremendous amount of spectrum available, and by some accounts, a gigahertz worth of spectrum in the 60 gigahertz band. But as I said, there's tremendous amount of loss. Basically, again, free space from 2 to 30 to 60 is a factor of 30 squared. You're pretty close to 30 dB right off the bat. Add for some minor blockage another 20 dB, and we have a 50 dB shortage. Basically, we're going to have to make that up with antenna gain. Now, my approach is a little different to other institutions. Doesn't suffice to say I can make it work in some cases. If we want to be successful providing equipment to real service operators, we need to aim for at least a attractive deployment scenario where we can ensure something like 90% coverage. Now, to give it some hope, I'm going to immediately abandon the idea of serving indoor users from outdoors with 60 millimeter 60 gigahertz, because we know it doesn't go through walls. So put that aside. There is still a lot of action on outdoor small cells. So think of lamppost high, small cell, illuminating an area of not more than 100-meter radius, but in a very high traffic, lot of activity like Times Square, like many downtowns of even small towns, where there is outdoor cafes, there is people sitting down at benches and having conversations and watching videos. But very high density of traffic generated because of the number of people, and also rich media in the future. That is the intersection of where it might still be interesting for a service provider to worry about and potentially pull some revenue out of it, and some exciting perhaps features that the technology could give us. Again, we cannot go kilometers. We know the physics are not there. And we cannot go in buildings. But can we at least achieve parity with 2 gigahertz on an outdoor near line of sight small cell with a radius up to 100 kilometers? That seems like maybe there is something there. So here is what I just said. If you go from 2 to 60, well, this is a little faint, but you can see that basically you have the 30 dB gap, depending on what model you use for non-line of sight, and how do you treat clatter, whether it's a dielectric slab or not, then you see that the 30 dB right of the Friis formula proportional to 1 of a square. So that's a bit of a sobering statement there. A lot of people say, well, let's just add antennas. Well, but it's very nice to look at the asymptotes. If the signal comes from a very narrow angular spread, think of it as a lighthouse, then as you make your antenna narrower and narrower, just cutting out noise. So that's perfect. You can take to the bank your antenna gain. That's fantastic. But if now put in fog, now that lighthouse, it's going to broaden, and you're going to see more of an area of penumbra. And at some point, the reducing your beam width at your antenna gain is going to be exactly canceled out by the energy you are no longer collecting, because it's not coming from a singular point anymore, it's coming from a region where there is local scattering. So through that process, you see that depending on the angular spread, you can still get plenty of gain, but the gain saturates if for a fixed antenna size, which actually means as we increase frequency, the beam width is getting smaller and smaller because as ratio to wavelength, of course, the antenna in wavelengths is becoming bigger and bigger. So think of it as the antenna getting bigger and bigger. And yet the gain saturates. You can achieve more gain at the base, but at the unit, at the remote unit or user unit, where the angular spread is much bigger because it may be bouncing back from another building, et cetera, the saturation phenomena happens even earlier. So this is giving us reasons to pause. We cannot just postulate, 30 dB, easy, put 1,000 elements. 50 dB, just go with even more elements. Antenna gain by itself could not be the full answer due to angular spread. So, again, the same type of analysis, but now specific to the 50 meters, and also now looking at line of sight versus non-line of sight. And you see how in the non-line of sight case, because of angular spread, the antenna gain as a function of frequency does not compensate for the increased pass longs, up around 4 gigahertz or something like that. It becomes a losing proposition. Now, we could say, and of course this is being talked a lot, let's consider the range equation. Now, as I said before, and I jumped to the punchline myself, if you do 1 kilometer, you have a huge SNR disadvantage. Or conversely, we can try and minimize the problem we're facing by just going through smaller and smaller ranges. As shown here, about 100 meters is the point where I say the service providers are going to be facing tremendous uphill battle to finance the densification of a network below that number. Why? Because it's not just about the box. Even the box can be for free. It's about backhaul, and it's about the owner of the building knowing that you're extracting revenue about that box, even if it's just attaching 4 screws or 1 screw, is going to want to cut in your revenue. So densification gets very tough as you get below 100 meters. I give you another personal opinion. As you go from 10 to 100 to 10 meters, then we have the entire Pandora box of unlicensed, customer-owned Wi-Fi type equipment that also available very soon at 60 gigahertz with WiGig and goes by .11 AG, I believe. Already devices are available, and probably this year we're going to have product available, probably sub $100, with the aim of covering sort of the 10-meter range. It doesn't have enough antenna gain to go farther, but at home you can replace your HDMI cables and go between your big screen and your DVD box. And so that's going to be an intense competition on the low end, short range. The very short range, in my opinion, is already spoken for. There'll be commercial product pretty soon. So that's why, as I mentioned before, 100 meter sounds like a reasonable sweet spot. And you still, you are talking about a lot of tens of dBs on our advantage, on the 60 gigahertz advantage, just because, at a huge price. We're cutting the addressable market to hopefully not a niche, but hopefully still a vibrant market segment. But clearly the ambitions are toned down from what it could be, going to macro cells and the like, which is certainly not viable. Okay. So, that's again the same story in non-line of sight with a reasonable transmit power at the small cell, by going from the 2 gigahertz reference point, we can go to the 60 gigahertz, but at a fraction of the range. So these are reasonable coverage goals, and in this one, even doing a 20 dB, well, we call it indoor penetration, but think of it also as even just one person in your main path at 60 gigahertz, its data is coming out telling us it's like a 20 dB blockage. So I don't want to overstate the indoor because, as we all know, and it wouldn't be reasonable to pretend going all the way to indoor. So reducing range is clearly something that we can exploit and take advantage of. Now, a lot of people have told us, no, it's we can use the full adaptivity of big arrays, and we solve the problem. All I said before could have applied, say, for point-to-point links, dish antennas. Just make your dish bigger, and you can get whatever gain you want. But in a non-line of sight environment, if you need to adapt, we're going to have phase arrays. So let's look at the issues with arrays. And also the opportunity of using wider bandwidth. I don't want to bother you reading the details, but also it's been argued that we can solve all the problems, but instead of going 10 megahertz typical 4G channels, let's go to hundreds of megahertz and everything will be cool. Well, let's give it a good look. In principle, this is the target we're trying to aim, and in line of sight, yeah, you added bandwidth, and your SNR is such that you can do a lot better. For instance, with 1,000 RF chains at 60 gigahertz, you achieve parity with only the same 10 megahertz bandwidth. So that is a sanity check. So if you use the same 10 megahertz at 2 gigahertz or at 60, then you need the 1,000 RF chains because we talked about the 30 dB, and you get that through 1,000 elements. But interestingly enough, you can get the same performance with only one RF chain if you now use something like 40, 60, 80 bandwidth. So in line of sight, adding bandwidth is huge, it's great. And the reason is simple. You get log 2 of 1 plus SNR. SNR is large. The rate has the B outside of the log. So if you are in the high SNR region, you're increasing rate proportional to bandwidth. So that is very powerful. In fact, that's why we do carrier aggregation in the 2 gigahertz band. We've gone from 10 to 20 to 40, 80, perhaps 100 in not too distant future. So the picture looks really exciting in terms of not needing to have exceedingly large number of elements in your phase array in high SNR line of sight region. But let's probe a little further to what it may be more of interesting from a business perspective. This is still outdoor, but non-line of sight. And I'm assuming a full adaptive array. And look at this, what's going on. That's our basic reference point again, at 2 gigahertz, 10 megahertz channel width. And look at how, depending on my number of antennas, the more antennas I have, it allows me to bring up the signal-to-noise ratio. Once I do that, then I can start climbing the log curve. But if I don't have enough chains, it turns out that it's very ineffective. So say with 1 to 10 RF chains, I just don't have enough SNR. And the log 2 of 1 plus SNR formula, if you just look inside the SNR, it's receive power divided by FKTB. The B there is bandwidth. If that fraction is comparable or smaller than 1, the whole fraction comes out of the log, and it completely cancels out the B that was multiplying your spectral efficiency to get to rates, and therefore, it's all there, of course. So that B goes out and cancels that B, and that's the asymptotic point you get there when the bandwidth goes to infinity. The really reason for be concerned here is that even at the bandwidth of interest, just because we're going non-line of sight, we're already in the low SNR regime unless we go into 100 RF chains or more. So this is starting to become a theme. The only way we're going to make it work, even though we could tap a gigahertz of bandwidth, but making reasonable assumptions about constant transmit power, not constant spectral density. Because if I can keep increasing the power as I increase the bandwidth, then I'm home, and like the line of sight case, and the B outside of the log is gonna just give me linear growth with bandwidth if I could keep the SNR inside the log large and constant. Looks like my batteries are dying here, but I think that's pretty obvious. If I can keep the SNR constant by increasing P as well as B, then it's linear. Rate is linear on bandwidth, then everything is hunky-dory. However, if I want to take this and do it a couple of orders of magnitude, it means that instead of the assumed few watts transmit power, I'm going to now be talking about 10 or 100 watts at 60 gigahertz, which is completely out of the questions again. So we're back to using a combination of large arrays as well as large bandwidth, but trying to maintain the SNR high enough through a short distance and high enough a number of elements to collect enough SNR. Now, if you add the number of dBs that would be appropriate into the building penetration, the news are so bad it's not even worth talking about it. It's this kind of slide that makes me very clear that if 60 gigahertz is going to work anywhere, it's going to have to be the quasi line of sight that I said before, like this here, this area here, the students are outside, you have lampposts, and maybe your main path gets blocked, but fully indoor coverage, it is completely out of the question, even using an unreasonable number of antenna elements and unreasonable amount of bandwidth. You really don't get much improvement because you're really buried under a very low SNR regime. So all of this is summarized in this chart here. And you see as we increase bandwidth and we play with the number of antennas, the black region here, it tells us where we are achieving parity with 2 gigahertz. So if we don't want to go the super wide bandwidth, like stick with 10 megahertz, then we're in the thousands of antenna elements. Initially we can cut that down dramatically until we've increased the bandwidth so much that we are in the low SNR regime, in which case, the antennas are increasingly less attractive. So here is the region we're going to be, and here is the region that it doesn't pay to be in 60 gigahertz. So bottom line is long roundabout, but hopefully rigorous, and believe me that behind it there are detailed studies with reasonable LTE-based assumptions about powered antennas and the like. Bottom line is, even with the incredible amount of bandwidth, even invoking hundreds of antennas, or rather, even invoking the huge bandwidth, we must be able to tap on phased array technology with hundreds of antennas. A year ago, I would stop here and say, hence, abandon ship. Well, I presented in various fora, and this is what's so exciting about scholarly dialogue. Several people took me to the side and said, you need to update your slides. Go talk to people doing RF integrated circuits in either pure silicon or silicon germanium. I said, I took that as a very positive comment, because really my views about antenna arrays not being feasible beyond, say, 20, 40 antennas came from an experience of 2 gigahertz, where things are big, and you use microstrips, and insertion loss are tremendous. And I confess my ignorance, I'm not a device guy, but I did take the effort to go and talk to people. So what can be done with antenna arrays in integrated form? Well, it turns out that in our own company, we have a team of fellows. You may have heard under the leadership of YK Chen. We are borrowing here on a tremendous advances that are actually being offspring of photonic electro drivers. So these guys are driving their lasers at the hundreds of gigahertz, and they are getting very good at designing integrated circuits on the electronic side. And so borrowing on that technology, these guys already published in that article there a device, silicon germanium, with 4 full magnitude control, phase control array on a chip. So you can connect out to an external antenna, a patch, and what's more exciting is that, well, I don't want to jump to my punchline, but I can tell you that it's full 4 branches, fully adaptive, phase and magnitude control, with good characteristics in the reception and in terms of the noise figure, and good power on the transmit side. And with very encouraging, there is a paper coming out, I don't want to steal their thunder, but there is of course, now they're in a race. If they can do 4, can they do 8? 16, 128. And I think we're just beginning to get the skills up and really extrapolate where we can go. Early discussions are very encouraging. I don't want to give any details until these guys, get a chance to publish. I think it's coming up in the Microwaves conference coming up very soon. But I am now of the opinion that silicon germanium and even pure silicon, when you look at what is achieved today, it is not out of the question to suggest that in 5 years' time, we could have single devices where you can have 16, 64 antennas, or active RF paths with individual magnitude and phase control. Of course, you want to be careful about what your baseband algorithm is going to be because, you're going to have all these computations to make. But pure silicon and computation, that seems to be the easy part. If we can solve the noise figure, the coupling losses, and also the total transmit power, notice that as we go more branches, the total transmit power actually gets easier because we are combining in the air, the per branch power is not so critical, right? If we want still get the same 1 watt out, but we have hundreds of branches, then with tens of milliwatts per branch, we're there. And so these guys have done a terrific job. They actually built circuits. Their particular implementation was actually for 90 gigahertz because, again, serendipity with millimeter wave imaging technology that is being pushed very hard, there is being a rush to commercialize that technology for like airport scanners and the like. And we have an interesting technology side effect that we could replay same designs from 90 down to 60. Actually, for them is even easier in terms of parasitic electronic design and the like. And they are telling me that it looks very doable. So stay tuned. System level measurements are already being performed on the 4 branch. Many more branches are planned and will be demonstrated and reported in the literature. And advanced modulation encoding, of course, is already assumed as, again, this borrowing technology from the millimeter wave imaging, but applying it in this case to 1632 QAM wireless link using real world integrated circuits and electronics. You see the constellation there, 10 gigabits per second, 8.7 gigabits per second. So in summary, I tell you a good story about the curious intellect and the scientific mind. We are never wrong. It's always a win-win. Having a scientific opinion, hopefully based on facts. If you're right, then of course it's always nice to be right. If you're wrong, hopefully somebody will point to where your misunderstanding is, and you will grow and learn by doing the additional research required. And humbly, that has been my experience in the area, a new area for me of 60 gigahertz. And I now am cautiously optimistic. I tell you that having now got to the point where we can no longer outright dismiss a large array as a feasible device. Of course, there is issues of cost and power consumption, but I'm sure those are almost secondary compared to the previous understanding of just not being able to put them together at all, just being infeasible. So what comes next? Well, you're going to have essentially sub-degree beams. That's the implication of 30 dB gain. And how do you find each other? So beam pointing becomes the next interesting question. If you're going to have M transmit beams and N receive beams, and notice something very important. You cannot give the beam gain to make the measurement. You cannot just say, oh, well, it's a M by N matrix, put a pilot on each element and measure sequentially or in parallel, because now you are not pointing anything. And if you're not pointing, you don't have the 30 dB gain, which means you cannot make your measurement. So you have to use the simple-minded approach of pointing in M transmit directions while listening into N receive directions and build up a table of what are your link gains in all possible M by N departure and arrival angles. That's much more modest than saying, I can give you the H matrix as in the MIMO space is usually discussed, and you can give me the optimal beamforming strategy, which, we would love to do that, because in a scattering environment, pointing in a single direction clearly is suboptimal. What if, in addition to that direction, you can bounce off that wall and you can bounce off the roof, and so you would like to do a generalized beamformer, one that is much filtered to the phase front of the whatever RF is getting impinging on your antenna. You do the conjugate beamformer, or even try to put a null in the direction of potential other users that you could be interfering with. All of those games presume that you have the knowledge of element by element complex gain. We don't have that privilege here. Our understanding so far, the beam pointing is really hard. We have a chance if we do it as beams, because then we can continue to count on the beam forming gain and have the link to a point where we can make the measurement in finite time. You can always build the channel estimation gain by waiting longer. But even that, you have to do it within coherence time, because the channel is going to change, and if you didn't finish your measurement for what could be a very large number of combinations, you are going to be in trouble. You may have to even repeat the measurements when you're using a very large bandwidth, because you also have a coherence bandwidth. So we have a coherence bandwidth and a coherence time to deal with, and we're in the process of trying to convince ourselves, is it possible to find the right combinations of departure and arrival angles that sustain a rate that is of interest. And I'm sure there'll be other problems after that. So it's a fascinating area, one that perhaps offers a new set of performance where a true 5G advantage and differentiating capabilities can be built upon. Thank you.